Okay, get your eye clickers ready. Nice to see everybody back. Maria mentioned the heat problem, and we're going to start working on it. We're going to continue with heat. We're going to have plenty of practice with it. But we're going to try to talk today about how to do another kind of tricky thermal problem, which is calculating the equilibrium temperature of two substances at different temperatures brought into thermal contact. Now, the very last item in the homework was about that. And we're going to try to extend that a little bit more today and finish it up on Thursday. You know, the past week, we have transitioned from basic dynamics. For instance, here's a photo of a student from the 9 o'clock section. And apparently, he went over with some friends to the Orlando Eye, and he is verifying the right hand. He's actually using his right hand for the right hand rule to represent the angular velocity and angular momentum of the Orlando Eye. I got to get down there. Now that stuff, you know, that's a fairly simple system. I mean, if you had to make it, it would be complicated. But as a system, it's fairly simple. It's just a circle going around and around in a circle. That's not too bodacious. But there are physical systems that are complex. And the reason that we're transitioning over to something complex like this is because we're applying the kinetic theory of matter, the molecular theory of matter, to massively populated systems. Like, think about this one. This is a famous photograph of a thunderstorm about to break out in the Sierra Nevada mountains out in California. And I love this photo because it shows, well, it's beautiful to look at, first of all. And second, it shows water. And it's got mountains. Those are made of rock, which is a lot of aluminum, a lot of oxygen, a lot of silicon, a bunch of other stuff mixed in. But other than that, look at all the water in this diagram. And we've been talking about water. We got solid water, all those patches of snow, the glaciers up on those mountains. It's solid water. The lake, liquid water. The thunderstorm is rising and boiling because of water vapor that's rising through the air. You can't see the water vapor unless you've got infrared. The clouds. Those clouds are in the updraft of the thermals. Those are water droplets. Did you know that that's the case? Every cloud that you see, other than like the really high ones, the cirrus, the ones that look like horse tails, those are actually ice crystals way up there. But most of the clouds, you know, like in a hurricane, most of the clouds in a regular thunderstorm, even fair weather clouds, is it raining out? Or is it still clear? Still pretty clear. So fair weather clouds, those are actually collections of micro droplets of liquid water, and they reflect sunlight. They look white, and when you look at a zillion of them, and they're so small, though, that the upward thermal draft just keeps them up there. And that's what you can see. This thing's boiling. This is convecting upward. It's a couple of convection cells in this picture. Do you ever see those ones like in NationalGeographic.com? They have pictures of supercell storms, and they look like they're spaceships from another planet, or under an alien invasion. But it's just a convection system, a complex, massively populated system of water molecules, basically, and oxygen molecules, nitrogen molecules that we call the atmosphere. And so here's another slide. Here's another complex system, the aurora borealis. And this one's viewed from space. Raise your hand if you've ever seen the northern lights, the aurora borealis. I have. Wow, nobody. The northern lights, aurora borealis. You've seen it? Yeah, it's cool. And I've seen it out in the first time I saw it, I was in northern Quebec, canoeing across northern Quebec, canoe trip. And it looked a little bit like this. I could see them way off in the distance along the horizon. We weren't that far north. But sometimes you can see northern lights all the way down in Texas. If there's a big coronal mass ejection or some kind of solar storm that hits our upper atmosphere, it'll light up the aurora borealis. It won't be the northern lights. It'll be to Texas. You can see them sometimes all the way down into Texas and Mexico, especially if you're up at elevation. And one time I was in Montana and I saw the northern lights. And I was walking out along a dirt road from my friend's house out to where I parked my truck. And I was just, it was dark. It was night, and it was dark, and I was just looking at the ground so I don't trip or anything. And then all of a sudden, I'm getting close to my truck, and I look up, and oh my goodness. From west to east, from north to south, the entire sky, and I'm up in the mountains, so I couldn't see the entire horizon, but the entire sky was filled with, shimmering and coiling and boiling red and orange, purple, green, blue light of the northern lights. And it's surprised. It gave me a start. I thought, oh my God, the Russians have nuked us. Because that's you guys, most of you grew up without having to worry about that. But when I was a kid, that was something that a lot of people worried about, and it's still a worry, but not as big a worry now. But if anything ever happens like that, you'll see it in the atmosphere. Anyways, but then I realized, no, it's the northern lights, and it was this. This is viewed from space. I think this is from the space shuttle. And we're able to study things like that thunderstorms in general, the northern lights, because of the kinetic theory of matter. So let's talk about some of the assumptions that we have in this kinetic theory of matter. First of all, and let's just restrict ourselves for now to a gas. Most of this stuff can be also applied to liquids and solids, but gas is easiest and most complete. An idealized gas is considered to be a collection of molecules. So, for instance, oxygen in the atmosphere that we're breathing is a diatomic molecule. There's two oxygens bonded together, two oxygen atoms. And that's what we breathe in, and then our body uses it. And a lot of nitrogen, 78%, something like that, is nitrogen. And nitrogen is diatomic as well. And then we get a little bit of CO2, and that's CO2. That's 3 atoms, triatomic. And there's a little bit of xenon and argon in our atmosphere. And those are noble gases that we'll study towards the end of the semester. Those are monoatomic. Okay, so helium. You go to the store and you buy a helium balloon. Helium is a single atom is considered a molecule of helium gas. So the kinetic theory of gas, kind of the idealized picture of a gas, is, first of all, we have a huge number of them. Now go ahead and write down the number 10, and then for the power, 10 to the 23rd power. That's a lot. So that's the typical number of atoms or molecules in a few grams of something. So 20 grams of oxygen gas, which is a lot of gas, that's going to be 10 to the 20, on the order of 10 to the 23rd, so scientific notation, something point something times 10 to the 23rd molecules of oxygen. Similarly for nitrogen. And there's no way that we can actually track all of them, or even one of them. We can't even track one in a gas. We can see some benzene and graphene, carbon centered molecules and atoms in solids I think at really low temperature, but a gas, forget about it. We can't even see a single one. So all this is supposition. It's our theory. It's our assumption. And what we try to do is, okay, we say there's a huge number, and we say that there's a random distribution of speeds. Okay? So there's some fast, there's some slow, there's some medium. So there's and all directions. So the velocities are randomized too. In a gas. Now in a liquid, they're not randomized completely. A lot of it's randomized, but a liquid will have some weak bonding. It will form droplets. A solid is not random at all. It's crystalline, or it's metallic lattice of some kind. Okay, so they're very strong bonding, very rigid bonding. That's why it's a solid. But in a gas, we consider it to be random, pretty random distribution of speeds, random distribution of kinetic energies as well. So a lot of different kinetic energy states, a lot of different momentum states. We think, our idealized picture of a gas, we think that they ricochet around like BBs. They bounce off each other, and they bounce off the walls of the container. And we forget about the gravitational interaction. The gravitational interaction compared to the all the BB action, all that bouncing and stuff is from electromagnetic repulsion, basically. Okay, and that's way stronger. Electromagnetism is way stronger than gravitation. For instance, the force between a proton and an electron in an atom, the electrical force that binds it into the atom is like 10 to the 40th power stronger than the gravitational interaction of the same proton and electron in the hydrogen atom. So we basically, you can write gravitation on the list and then cross it off because we just kind of neglect that. And then the other thing we it's almost like a supposition or hypothesis. We say that F equals ma works for everything. F delta T equals delta P. 1/2 mv squared for the kinetic energy, etc., etc. And when we do that, when we proceed under those and try to figure out an average, and these assumptions here, A, B, C, and D, you can write down a mathematical expression that matches the English sentence that you've got up there. Now, I'm not going to do that because to do that, you would have to do a ton of calculus, a ton of trig, and a ton of stats. And so we're not going to do any of that. But we are going to state the results, and that is that the kinetic energies, when you look at those, there's a big range of those, slow to fast, but they have an average value. There's only one average for the there's if you average anything, if you average, you go to the shore and you scoop up 200 grains of sand and then measure the mass on a really good scale, and then add up the total masses and then divide by how many you got, then you'll have an average. And it's just one, number. So average is what we call a central measure, and there's only one average in a given collection of particles, a given complex system. And what we find is that the average kinetic energy is proportional to the temperature in the Kelvin scale. And we've mentioned that in the past, that the temperature Kelvin is proportional to the positive Kelvin temperature is proportional to the positive kinetic energy average in a gas. And something similar to that is true in a liquid and in a solid. It's a little trickier. But for a gas, it's fairly easy to do. Right? So this is the kinetic theory of gas, and we've figured out that, the things that we can measure, the pressure, the temperature, the density, all those things work out, and they verify assumptions A, B, C, and D. We're really on the right track. Now, it's not perfect, because we're, for instance, ignoring gravitation. The other thing that we're ignoring is nuclear forces. But most of the time, for a gas, you don't have to worry about that, unless the gas that you're studying is the hydrogen and helium in the core of the sun. And under those conditions, you get nuclear fusion, a nuclear reaction. But other than that, this is a pretty good set of assumptions for gases in the human scale of things. Now, the distribution of the energies forms a curve. Go ahead and write this sentence down. We have a random set of directions, but the distribution, once you say that you're using the kinetic theory of gas, the distribution of energies and speeds, it doesn't really stay completely random. It arrays itself into a curve, and this is the curve. This is called the MAXWELL-BOLTZMANN distribution. In the vertical scale is the number of particles or molecules in your gas. On the bottom, the horizontal scale, is the speed. So slower on the left, faster on the right. And if you do all the F equals ma and kinetic energy and a bunch of calculus, a bunch of trig, a bunch of stats, you come up with this, and then you say, all right, for every energy, I'm going to calculate how many particles theoretically my gas has got at that energy. So it follows the shape. So let me get my cursor. My cursor's tiny. Sorry about that. So over here on the left side, this is the slow side. Go ahead and sketch this distribution. And notice that it's not symmetrical. Don't make it symmetric. Don't make it a bell-shaped curve. It's a completely different distribution. That's called the Gaussian distribution. This is the Maxwell-Boltzmann. On the left side, the slow side, it's pretty steep. So if this were a mountain, this would be the steep side of the mountain. Now over here on the fast side, it's still pretty steep, but it's not as steep. Okay, so this drops a little bit more slowly. So what that tells you is that if you go to the center, the peak, so this is the most highly populated speed. Right? So in this hypothetical gas, molecules or atoms of this speed are going to be the most numerous. That's what peak means. Okay? Now, if you go 10 meters per second to the right, that's over here in the high speed area, you're going to have a certain number. And if you go 10 meters per second slower, that's over here to the left of the peak, you're going to have a certain, and it's going to be different. And because it's steeper, on the left, on the slow side, that means that there's slightly fewer slow particles. to the left of the peak. All right? So if you go out 10 meters to the left, it's dipped down quite a bit. All right? So right here, 10 meters horizontally, 10 meters per second horizontally is going to be a lower, and over here, 10 meters per second horizontally, you're going to be up here a little bit higher. And that's because the curve is not perfectly symmetric. It's not as steep on the high speed side. And that's just a result of all the calculus, trig, and F equals ma and stats that you apply to this. All right? And for that reason, the average speed is going to be over here. Okay, so this is the most numerous. This is what you would call the mode. Okay? And the average is over here. All right, you add them all up, add up their speeds, and multiply by how many you got, and then divide all of that by how many particles, the total number, and you'll get this average speed. And you got to do a lot of calculus for that, so we're not going to get into all the calculus of that, but what we are going to do is take a look at why this, or how we would use this. And here's the picture. So this is the Boltzmann distribution. And the average speed here is what we got. We could do a similar distribution for kinetic energies. All right, so this is speed. 1/2 mv squared. We could do a 1/2 mv squared curve and get an average kinetic energy. And then that's the one that would be, proportional to Kelvin temperature. And why is that important? Because the shape changes with temperature. So in this particular diagram, now this one, I don't want you to worry about some of this stuff, but do look at the two curves. Similar vertical scale is proportional to the number of atoms at a specific speed, and the speed is down here. 2,000 meters per second here, 4,000 meters per second here, 6,000 here. So you can see that this blue curve, that corresponds to a gas at 273. All right, so that's 0 Kelvin, or 0 Celsius. All right, so standard temperature and pressure. Now that's got a lot of particles down here at this, but this is less than 2,000 meters per second. So it's most highly for this, and this is helium gas, all right, which is monoatomic. Helium is a noble gas most of the time. And so its average speed at 273, the freezing point of water, it's not the freezing point of helium, but it's the freezing point of water. It's down here, I don't know, about 1,800 or so, right here. And there's a lot near 1,800. But look at down here. At 4,000 meters per second, zip, zap. Maybe you got a few down here, but it's so small it looks like it's 0. This is like 5. Whereas up here is, something times 10 to the 23 or something like that. Right? And then down here, and notice that down here at even lower, so here's 1,000 right here. Now look, see where my cursor is down here? I've got it right below the tick mark for 1,000. Now look at the red curve. The red curve corresponds to 2,000 Kelvin, and that's pretty hot. Okay, way hotter than a furnace. Maybe welders use I'd have to look that up. Welder might have an arc welder that is that hot. But at any rate, at 1,000 Kelvin, where my cursor is down there, look how high the blue curve is above the red curve. Now the red curve is hotter. It's a hotter object, or it's a hotter temperature of gas, but it doesn't have as many, so above 1,000, it's the red gas is here, but above 1,000, you got to go way up here, right about here. It's about 3 times as many for the 273 Kelvin gas. All right? So these distributions are temperature dependent. The cooler the gas, the sharper the peak. Go ahead and write that down. The cooler the gas, the sharper the peak. The hotter the gas, the broader the peak. You got a lot more random speeds and stuff. You still have one peak speed, and if you did kinetic energies, you'd have one peak kinetic energy, one average kinetic energy. Now, for those of you that are saying, Dr. B, how does the temperature affect, how is this temperature dependent? Well, here's the formula. These things are this is what we call a probability density function. So that's like from stats class, so don't worry about that. It's basically proportional to the number of particles at each state, okay? And that function, look at this. Look at this jazz we got down here for the function. I got an exponential function, e to the blah, 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 and then look where the temperature is. E to the big exponent, and the exponent is a quotient, and the temperature is in the denominator of the quotient of that exponent of an exponential function. Now, for those of you that haven't had calculus or pre-calculus, you probably are thinking to yourself, Dr. B, what's e to the, what's that? It's a calculus function that is used everywhere, but we don't have to worry about it. I want you to see it, see how complicated it is, but wait, there's still more. We got another factor of t in here. Look at this one, right down here. It's in the denominator of this square bracket, and the square bracket is to the 3/2 power. Oh my goodness. So we got a really complicated. Are you supposed to be a hound dog with a motorcycle helmet? Nice. Very nice. Lovely. Is anybody else in costume? I didn't notice. Only one man brave enough to come in a costume. Well, that's all right, because I got a scary pumpkin up here, so it's, so now look, this is, so for those of you guys that have calculus, I could calculate this. You guys could probably do it. It'd be a lot of work. But, so when I say that it's temperature dependent, this is how it looks. It's bodacious. We're not going to have to worry about it. All you can do is, it's like seeing a picture in the newspaper of some epic fail that somebody, like coming to class dressed as a hound dog with a motorcycle helmet, which is not an epic fail, but it's notable, but not everybody's going to want to do that. So, but what I do want you to remember is the shape. The shape is temperature dependent. The energies and the speeds, they form a curve. The curve is temperature dependent. So this big fancy formula down here, just kind of dim that out of your mind. I'm now giving you permission to just dim that out. And this Maxwell-Boltzmann distribution, just remember kind of the shape of it, and that it changes with temperature. It broadens out as it gets hotter, and it gets sharper and taller as it gets cooler. The temperature is cooler. Stuff. And it'll look different if you change to a different gas. So from helium, if you change to oxygen, or nitrogen gas, N2 or O2 gas, it'll be a little different, but it looks something like that. Now, we've talked about Max Planck before, and I want to mention how he starts to fit into this discussion. This discussion of distribution of energies. Well, Max Planck was studying thermodynamics, but what he was studying was the color of light given off by hot objects. So, You stick something in the campfire, or you turn on your burner at home. If you have an electric range, and eventually, if you turn it up to high, you'll get it up to red hot. Your campfire, you put some metal in there, you can get it red hot and stuff like that. And that's the kind of stuff that Max Planck was studying, color and temperature. Now, we're going to start getting specific, and this is pretty much all I've ever told you about Max Planck and his famous constant H. But we're going to get a little bit more into his work now, because it's starting to bring. And this constant H, Max Planck and his constant H, is going to be one of those things that we're going to be talking about until the end of the semester. So we're F equals ma, F delta x, work, Planck's constant H. Any given day between now and December, we'll be talking about maybe all three of them. Now, he was studying thermal physics under the kinetic theory, and he was trying to put it all together. And what he was studying was, he was measuring the intensity, the amount of joules per second at each wavelength. So if you took something that's red hot in your kitchen, and then put the light, beam that light into a prism or some other dispersion device, and split the spectrum up, you'll see it's got some reds, some deep reds, some orangey reds, some oranges, maybe some yellows, but not a lot of greens, blues, or violets. Okay? If you heat something up till it's white hot, and then put the light from it through a prism, like the SUN, the SUN's got all the colors of the rainbow. And you can, and if you put sunlight through a prism, the temperature of the sun is about 5,800 Kelvin. All right? Really, really hot. The surface of the sun. The part that provides sunlight to us is about 5,800 Kelvin, really hot. And it produces a lot of energy in all the colors. There's a famous scientist named Roy G. Biv. His middle initial is G. And his last name is Biv, B-I-V. Very easy name, Roy G. Biv. And Roy G. Biv is famous because, you know how some people, when they die, they donate their body to science? They take the body and they go to med school with it, do stuff with it, for med students and stuff. So you die, you donate your body to science, right? Roy G. Biv, when he died, he donated his name to science. Because Roy G. Biv just happens to be the exact order of the colors. How did his parents know that when they named him? But anyways, it's the exact order of the colors in the electromagnetic spectrum in sunlight. Red, orange, yellow, green, his middle initial, blue, indigo, and violet. Now, I don't know what color I don't know the difference between blue and indigo or violet and indigo. But apparently Roy G. Biv's parents knew. And their family way back in Slobovia or wherever they were from. So Roy G. Biv, that's the order of the colors in the spectrum. All right? So Max Planck is measuring. Okay, so he's measuring the intensity. How many joules per second? Red. How many joules per second? Orange. How many joules per second? Yellow. How many joules per second? Green. How many, and on up. And probably he was measuring infrared and probably measuring some ultraviolet, because they could do that. And we could do it way better now. And he was probably measuring, different wavelengths. So red corresponds to a set of different wavelengths of light, and orange a different set. And so he's probably measuring even more precisely than that. And the thing is, and other people were doing the same. And they couldn't make sense of it. All right? So he was trying to figure out the theoretical theory of what they had observed. So he said, all right, I'm going to make a model of matter, and I'm going to idealize it. And so his idealization was, okay, I'm going to take some hypothetical object, I'm going to call it a black body, and I'm going to attribute to this object the perfect properties, specifically that it's a perfect absorber. So it's a black body. It absorbs every color of light perfectly. It doesn't reflect any. It absorbs it all. So we got a fellow up here in the front row. What's your first name with the red shirt? Adam. Can you stand up a little bit? So people. Yeah, stand all the way up. Stand all the way up. You did it. Nice. And Adam's got a red shirt. Right? But if we turn out the lights, okay, good, thanks. Adam, yeah, you can sit down now. We're good, yeah, you did it. All you had to do was stand up. What a demo. You did it, man. So anyways, if we turn out the lights, which I'm not going to do, but if we did, you couldn't tell what color he has. The reason that you can tell he has a red shirt is because that fabric, the dyes in that fabric, reflect a lot of red, and they probably reflect a few other colors. But if you put the light reflecting from his T-shirt into a prism, you'd find a lot of joules per second for reds, but not much for O, Y, G, BIV. And maybe a little. Now, let me see if I can see anybody with a. Okay, young lady on the aisle with the green top. What is your first name? Maria. Could you stand up, Maria? Thanks, Maria. Now, Maria's wearing a green jacket, a green kind of sweater, I guess. Just trying to stay warm. You're from Florida, right? From Miami? Where? Lakeland? Okay. The reason I could tell she's from Florida is because if you were like from New Jersey or somewhere up there, you'd be in shorts and T-shirt in this kind of weather. But people from Florida, they start bundling up now. Now it's getting 70 degrees. You got to bundle up. Anyways, that's green. So her sweater. Okay, thanks, Maria. You can sit down now. Maria's green sweater, and I see a guy over here on the aisle with a yellow, Damien, and a guy 3 seats behind him in a blue shirt with he's not even paying attention. Now he's paying attention. And the color that you see is because that color is reflected from the dye molecules in the cloth, and that's what you see. But if there's no light reflecting off it, you ever hear that saying, all cats are gray at night? It's the same thing. If we turn the lights out of here, everybody would look like they have gray clothing on. Yeah, or black, because it'd be pretty. There's no windows in here, so everything would be, it'd be pandemonium. You wouldn't be able to see, So a perfect absorber of radiation is not going to reflect any color. So we call it a black body. All right? And by the same token, it has to be a perfect emitter of radiation. Now, this is not reflecting. We're saying that, it's a substance, a piece of metal or something, and it's emitting light because it's hot. For instance, the filament of an incandescent light bulb, which I think we got a few up here. Those are the old-timey light bulbs that are hard to buy now. They used to be pretty nice. And they have a little wire in there, and it gets hot, and it emits light because it's hot. Thermal radiation. Okay? And a black body, so Max Planck is thinking, all right, let me think of all the little particles, all the little atoms and molecules in a black body. And he said, they're going to be oscillating back and forth, back and forth, back and forth. And as they oscillate, they're going to emit electromagnetic radiation. And I'll show you why that's the case in a couple weeks when we study electromagnetism. But he said, all right, so I got this black body, and, I've got to figure out how to get this kind of a spectrum from a black body. Now, here's what they observed. Now, this is it looks like a Maxwell-Boltzmann distribution of speeds. It's not. The horizontal axis is the wavelength. And the vertical axis is the amount of energy in each nanometer of wavelength. All right, so what they do is, this is like Max Planck saying, okay, I'm going to measure the joules per second at red, the joules per second at orange, the joules per second at yellow, green, blue, indigo, and violet. And probably, this one is taking watts per second for, 10 different wavelengths of red and 10 different wavelengths of orange, because these are pretty nice curves. All right, now here's visible light. The horizontal scale is the wavelength of light. We'll be talking about waves and stuff in a week, maybe Thursday. That greenish window with the red edges, that's the wavelength band for visible light. Okay? Now here are the boundaries. You might want to jot this down in your notes. The wavelength boundaries in nanometers for visible light are 400 nanometers for us. 400 nanometers up to about 700 nanometers. And you can see that's where, if you're up close, or if you look at this on YouTube, you'll see that that's where I've plotted this kind of greenish window. All right? Now, the spectrum, these curves they don't show a distribution of speed. What they do is they show a distribution of intensity of light from these black bodies. Now, I've done this in the lab myself. We took a well-insulated, basically a box, and lined it with ceramic tiles that could withstand really intense heat. And the ceramic tiles, we had coils of really tough electrical wiring. And just like, inside, I'm trying to think. You know what? I think a hairdryer has coils in it. Okay? And those coils, they put electrical current through it. They get red hot. They produce a lot of heat. And then the fan blows air through it, and then you dry off your hair, right? And so what we had was we just basically had a box, and we had it lined with ceramic that could withstand a lot of heat. We heated it up really high, like 1,000 Kelvin. And then we measured the intensity of, 10 reds, and then the next 10 oranges, and then the next 10 yellows, et cetera, et cetera. And we did some ultraviolet, and we did some infrared. And we mapped out the intensity. And it changes by temperature. Now, this means, so that this big curve, the red curve, that's for a black body that's at 5,500 Kelvin. Now, the sun is just a little bit hotter than that. It's about 5,800 Kelvin. This green curve right here where my cursor is, the second one down, that's 5,000. This next one, the middle one, the third in the series of 5, temperature 4,500. This is kind of bluish one or purpley one. All right? And notice that as the temperature goes down for this black body that you've heated up with electricity or however you're heating it up, it gets shorter. Also, the peak shifts to the right. Now see here, temperature of 5,500, the peak is up here, and it's kind of in the middle of the visible band. All right? And the sun actually is in the middle of the visible band, 5,800. 5,000 is a little bit cooler, and notice that the peak is shifted a little bit to the right, and it's lower down, Maria. And then 4,500, whoa! You're a lot lower, and you're shifted to the right. Your peak is still in the visible, but you know what this one would look like? The peak color is down in the 600s or 700, so this would be reddish. You know, the peak color here is red. The peak color here for 5,500 is kind of greenish blue, right? And then now look at 4,000. Whoa! Peak color is maybe at 700 nanometers red, the deepest red that we can see. You know, they say that some animals can see a little bit into the infrared, and probably some people in here can see a little bit. But for the the rule of thumb is 400 violet, 700 red. And look at 3,500. The peak is really low. Another 500 Kelvin down, and guess what? This one, you'd see some red. You know, it's on the scoreboard here in the visible, but guess where its peak is? It's out here. And this right-hand side, go ahead and mark it on your notes. The right-hand side to the right of visible on this graph, infrared. And so the peak of this one, it's so cool, it'll show up in the infrared as the peak color. But it's still going to look red to your eye, because you're still going to see. And look at this: the most visible light that you see is red. The least is down here at 400, and that's the violet end. So you're seeing some violet, and if you put it through a prism, you'd see some violet, and you'd see mostly red. But if you had an infrared prism, you'd see that it's even brighter in the infrared, near infrared. All right? And just so you know, these are the surface temperatures. These could be the surface temperatures of a bunch of stars. Like I talked to you last time about Betelgeuse, the supergiant in the right shoulder of the constellation Orion, which you can observe after dinner right now, if the skies are clear. You know, he might have a surface temperature of about 4,000 or so. It's really red. So in 1900, Max Planck came up with this theory of black body radiation. You know, how do you get those curves? They look like the Maxwell-Boltzmann distribution, but it's radiation intensity. So he decided that he's going to add this one little proviso to his model of black body. You know, so all the same things as before, F equals ma works. And he said, I'm going to make it so that the energy of those particles that are oscillating back and forth in the black body, and as they oscillate, they produce light of various colors. He said, I'm going to make the energy proportional to a constant. And that's Planck's constant, the quantum of energy in the black body. And it's actually the frequency of the radiation, not its wavelength, times h. And that's the energy of each of the little atomic or molecular oscillators in the black body. Now, with this, I just turned off my mic, hold on. With this, he explained those peaks in the spectra. He got them to work just where he wanted. And he also began the quantum science revolution. Now, this is 1900, so 118 years ago. And we're still in the middle of it. We haven't figured out everything. Don't let scientists and engineers, snow you. You should be humble. Scientists, the normal, and the best scientists are humble. Like Max Planck. He looks like a banker. From some old movie with Charlie Chaplin, from the 1920s. He doesn't look, like scientists nowadays, they like to think of themselves as wild and crazy and unconventional and stuff. Wild hair and stuff like Einstein, which is a bunch of bull. But anyways, Max Planck, he looked like a banker. Now, here's the thing that he figured out. He figured out why these spectra, and I hope you've drawn at least 2 or 3 of these. He figured them out. And here's the thing about it. Before Planck figured it out, there were guys that could handle the infrared side over here. The large wavelength side. They figured out a theory, and it was black body theory, but it didn't require the quantization of energy that Max Planck did. And they could figure this out. They had a good lock on it. But they couldn't make the spectrum start down here and then dip back down to 0, zip zap over here. And then there was other guys that they had a theory of black body radiation that could explain the uphill slope on the left. Now, this is the ultraviolet side over here on the left. Right? There were guys that had that side, but they couldn't get it to bend back down and dip down in the infrared. But Max Planck, he nailed it. So all this stuff that he came up with, his constant H, it rose in terms of quantization of energy. He figured out the spectrum, and the implications of that led to the entire quantum revolution that we're still in the middle of. Now, here's a short table of some other temperatures that we talk about from time to time. Room temperature, 290. Yeah, that has a peak in the infrared. So if you're looking at a blob of gas at room temperature, you won't really see much in the visible. Look, we're in a gas at, about 290 or so right now, room temperature, and it's transparent. But in infrared, you'd pick it up if you have the right infrared scanner. Human body, 310, infrared. Standard temperature and pressure, STP, that's from chemistry class, 273 Kelvin, infrared. Even Mount Everest on a cold night, 238 Kelvin, pretty cold up there, infrared. And if you think about it, this is why the Army guys, use night vision goggles, because at night, and unless you're like down in a jungle where the nighttime temperature is still in the 90s, if you're out in the desert, for instance, the desert gets cool at night, and even Orlando gets cool at night, a few degrees. So if you see somebody that's 98, their peak wavelength is a different wavelength than the air around it and the surface objects around it. Out in the desert, it gets really cold at night. So they can pick stuff up with infrared goggles. But now the surface of the SUN, 5,800 Kelvin. Oh, my goodness. And you know what the peak energy is there? Green. The sun is green. To us, it looks white. That's how our brain processes it. But yeah, the peak color is actually green, which is kind of interesting. The most abundant color of the most abundant energy from the sun is green. The sun puts out a lot of red, puts out a lot of violet, but the most it puts out is green, which is kind of an interesting conundrum if you think about it in terms of plants. Plants are green, right? To your eye. And you might think, oh, nice, evolution, sweet. It's using the most energy, the color of the sun that's got the most energy in it. Good. But you're not thinking right. You see it as green because it's reflecting more green light than anything else. It ain't using it for chlorophyll and photosynthesis. It's reflecting it. It's rejecting it. But apparently that's some kind of a evolutionary advantage. I've never read the reason for that, but and there's other plants that are not green, but all the green plants. It's kind of strange. I'm sure I'll have to try to look it up. I'm sure somebody's figured out why. All right, let's do an application of kinetic theory. Get your clicker ready. I have a clicker question for you. Here it is, ammonia. Very specific quality. If you've ever observed your family using ammonia, like in the kitchen, just read carefully and think. April. Clicking? Excellent. Just double checking. Students, I just calculated before class, this is the 50th question of the semester since we started officially. It was 37 last week. We're now up to 50. This is number 50. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Yeah, most of you got it right. 77%. Yeah, ammonia is pungent. Now, in terms of the kinetic theory, here's what you'll see. That smell, it'll diffuse through a room much more quickly if the room is hot. Because the ammonia gas that you smell in your nose is a gas, and it'll equilibrate with the room temperature. It'll evaporate off the surface. All right? And then it's a gas. It evaporates. The vapor exits the liquid. Right? And then eventually it gets over to your nose. And if you're 10 feet away from the bottle of ammonia and somebody uncaps it, then you'll smell it faster in a hot room like this than in a room, up in Maine that's like 40 degrees instead of 70 degrees. All right? And that's an example of the average kinetic energy being proportional to the Kelvin temperature. All right? And, so as the room fills with ammonia, eventually you'll smell it. And it's random motions. It is a gas. And zillions of kinetic energy states. But there's only one average kinetic energy value, and that is proportional to the Kelvin temperature. All right, so that's a simple application of kinetic theory in terms of things that you can observe with your nose. And they say that if you are afraid of dogs and you want to be ready if a bad dog in your neighborhood comes around, have a squirt gun filled with ammonia, some kind of ammonia solution. And they hate that. Squirt it at the dog and they'll really hate it. Because they have ultra-sensitive noses. So for a dog, it'd be like blasting, a huge speed, putting you like 2 inches from a speaker and then revving it up to 11, playing some really loud music. It'd, burn your eardrums. You'd want to flee. And apparently that's what dogs do. All right, let's talk about heat transport. Now, I'm going to ask a question here. Yes? To this one? Oh, you mean you're copying notes? The same notes that are in YouTube in about an hour? Okay, hopefully you got what you need. Okay, heat transport. You get it from YouTube. Don't worry. You know, and by the way, I was talking to somebody in the first hour that she has started studying and revising her notes, re-listening to YouTube and filling in her notes after class. And apparently it's a good study technique because she went from a medium grade to crushing exam 2. So, and my TA, Darian, from previous semesters used to do that same thing. All right, heat transport. So, you know, the ammonia is going to transport itself. That's a molecular transport because of the thermal conditions. Let's talk about the transport of heat energy itself. Now, these are the 3 principal modes: conduction, convection, and radiation. And I love this picture of the fire breather because it shows all 3 modes of transport. By the way, is there anybody in here that's actually ever seen this in real life? Somebody doing this? All right, show of hands of who's done it. Rachel, you say you've done it? Who else? Anybody? You know, there was somebody in the first hour class, and today is the first time I've ever had anybody say, yes, I've done it. So let's talk about it. Here's a guy. So what you do is you put the kerosene in your mouth, and then, as soon as you can, you blurt it out. You go, you get it into little droplets coming out of your mouth, and then you torch it. That's just like this guy. See, he's got a little torch in his right hand. If he doesn't have that, he doesn't have, he's just blurping it out for no reason. Right, Rachel? Yeah, you got to have some kind of a light, some kind of a flame to touch off the kerosene vapors. Now, you're blurting liquid kerosene out of your mouth. And the reason you try to make it into little droplets, in other words, you don't go like this. You don't, make one big stream out of your mouth. You try to make little droplets coming out of your mouth because the droplets will evaporate more readily, ounce for ounce, gram for gram, than a straight stream. There's more surface area, the more droplets you can have. The more surface area, the more kerosene vapor. The more kerosene vapor, the easier it is to torch it off. And that's what this guy's done. So he has to have physical contact of hot with cold. And the heat flows into the cooler object relatively easily. All right? And it raises the temperature of the cooler object. So that's what he's got in his right hand here, that torch. And if he does it right, hopefully he doesn't blow it, he's got a nice little fireball there. All right? So he's got to use some kind of torch because, he can't, hopefully this is obvious, but he can't have the kerosene already on fire in his mouth, obviously. That would be a disaster. All right? So now, a counterexample to the idea of conduction is an insulator. And an insulator is a substance that'll conduct heat, but not really very well. And guess what? Air is a really good insulator. All right? And I'm looking around the classroom, and I see a bunch of people with sweatshirts on, and I don't see anybody with a parka. I saw a few people last week wearing parkas. With the quilting and everything for the cooler weather that we've been having the last few days, which is nice. And the reason that works is because they trap air. If you have a down comforter, it's not the down. It's the fact that the down traps air. It's fluffy. It's thick and nice. A sleeping bag, usually made with down or maybe with synthetic polyester fiber fill. The polyester has the added advantage that it'll insulate even when it's wet. Whereas down, of course, won't. But it traps air. A fleece, same thing. Any kind of, when you put on winter mittens or gloves or something like that. And what that means is the heat source is your hand or your body. And you're encasing your body with air. And the down allows you to do that. The polyester, the quilting allows you to do that. It traps the air. And then the heat, if you're just, walking around in a t-shirt, there's going to be a lot of heat that goes from your body into the atmosphere. You're warming up the atmosphere. It's cold, you're hot, you're warming it up, and you're cooling yourself down. You're freezing your you-know-what off. Okay, if it's cold enough. But if you put on some fleece and stuff, you'll still lose heat, but it won't be nearly as quick. All right, so that's an insulator. And there's all kinds of things that'll insulate. Even some kinds of steel. A stainless steel, there's varieties of stainless steel that you can put it into a campfire or any kind of heat source and get one end of it red hot, and then 12 inches, 18 inches away, you can actually handle that piece of steel with your bare hands, versus a piece of standard rebar, from concrete or any kind of construction. That's not fancy steel. It's strong, but it's not fancy, and it'll conduct heat all the way through. And it has thermal properties for that reason. It's sometimes nice to have good conductors of heat in your construction. Second mode, convection. Now, convection is a form of bulk motion. And the conditions for convection are the following: that you're surrounded by something that's not a good conductor, like an insulator, like air. And that's what we've got in this picture. He's blobbing out that fireball, but around the fireball is air. So there's going to be heat conducted into the air. And, if you were over there, you'd feel it. If you were fairly close to that guy, you'd feel it. But it's not that rapid, and it's so slow that it gives time for that fireball to rise up in the air. And why is that? Well, because it's hotter. Usually stuff that's hotter is less dense. Here's another example. Hot air balloon. Raise your hand if you've ever ridden in a hot air balloon. Okay, a few of you, good. And when you're in a hot air balloon, what do? There's a guy up there, and the guy that's in charge, and he's got the propane burner, and every few minutes he blasts out another blast of flames. And that's because this hot air balloon, it will conduct out into the surrounding air slowly. And so he's got to reheat it and keep it going upwards. And then when they want to come down, they just, let it cool off a little bit. All right? So there's a buoyancy force, a net buoyancy. The air is going to be, like this one, it's probably 70 or 80 degrees out there on that plaza where that guy is. Okay? And the temperature of that fireball is going to be hundreds or even 1,000 Kelvin. It's really hot. All right? And therefore it's going to be more buoyant, less dense, and it'll rise upward. So even the earth, the mantle of the earth has convection cells in it. A thunderstorm is a convection cell. It's convection of heat upward into the atmosphere in the heat vapor and the hot air that goes with it, and then eventually it gets to a certain altitude and then it forms a cloud because it's cold enough to recondense the water vapor into liquid water droplets. But Yellowstone National Park out in Wyoming, Montana, and Idaho, they have all those geysers and stuff. That's actually the location of a plume of energy rising off the core of the earth through the mantle and all the way up to the surface. And here's a picture of it. They figured this out from using a bunch of seismometers around Yellowstone. You know, I used to live out there about 40 miles from Yellowstone, and it's kind of a cool place. And they have a lot of earthquakes all the time, small ones, but they're measurable. And because there's so many, if they have seismometers, you know what it's like? It's like sonar. You know, you can measure the sonar. If you have 2 sonar stations, you can triangulate on the source, or you can even find places where, you know, the water density changes if you analyze your sonar correctly. And the Navy does that all the time. And the same thing here. They listen to these seismometers, and they figure out, well, there's a place here where the seismic waves are going more slowly. And that's where they figure the rock is more liquefied, therefore hotter. And so they can see it. And this is a side view. So down here at the bottom of this gray graph here is 800 kilometers down. All right, now that's a good fraction of the way to the center of the earth. And up here at 0, that's out in Wyoming. That's where capital Y is. And so you can see there's a big pool of really hot molten lava up here near the surface. And that's what causes all the geysers and stuff. And here's another view from a different angle. This one's looking from northeast to southwest. And this one over here is looking northwest to southeast. And so different angles on the same plume. And you know, they've been looking at this for years now. The Yellowstone mantle plume. Here's another mantle plume, Hawaii. You know, we've got volcanoes and stuff, and Yellowstone is a gigantic it's a super volcano, they call it. If it ever blows again, hopefully not in our lifetime, it'll destroy most of North America. It'll kill a lot of people because a lot of volcanic ash will fall. And all our farms in the Midwest, well, depending on which way the wind is blowing, they'll be, you know, kill all the animals, kill all the crops. It'll be a real disaster. Hopefully it won't happen. But anyways, Yellowstone, we're in the middle of the continent of North America. And you know, the ring of fire, that's all around the Pacific. You know, from Indonesia all the way up to Alaska and all the way back around through Japan and all the way back down to Indonesia. Those volcanoes down there, they're because of the continental plates trying to force their way over or under the Pacific plate. But not Yellowstone. Another place, Hawaii, it's out in the middle of the ocean. It's not by the rim. There's a couple other places on Earth where we see these plumes. And, you know, we're going to have to study waves and oscillations in our next chapter. But let's get back to thermal stuff here. Just a few more notes, and then we'll dismiss. Radiation. Radiation is basically the transport of energy, not by convection, but photon by photon, from like the sun to Earth. And each photon of sunlight carries momentum and energy. All right? And then if you absorb it, you know, you'll absorb some energy. So, and radiation can be of any wavelength. So it could be radio frequency, infrared, ultraviolet, X-ray. You know, those will all heat and cool. If you're losing a lot of X-ray and ultraviolet, it'll cool your object down. So if the material absorbs it, it'll heat it up. Okay, so for instance, your skin cells, they'll absorb ultraviolet and you'll get sunburn, which is a chemical reaction, I guess, or even skin cancer. It can mutate some of your skin cells and you get skin cancer. And you know, even astronauts like this guy on the moon, they have to protect themselves from sun, because the sun you know, out at our distance, the sun and the moon and the earth are about the same distance from the sun. We get about 1,370 joules per second for every square meter that's in the sunlight and facing toward the sun. So the space program has to use stuff to defeat the solar heat gain. They use mylar, you know, this reflective plastic. It looks silvery because it's trying to reflect everything. Here's another thing that they use. You know, the astronauts, they have to have gold-plated visors for their helmets because the gold will reflect most of the solar heat gain. They'll still be able to see through it. It's thin enough that they can see through it. But they don't want all, because there's no atmosphere on the moon, so they get everything. And then compare that to something on the roof. You know, your solar energy collector for a hot water system, you want that to accept as much photon energy and momentum as possible. Right? We'll talk about SR-71 Blackbird on Thursday. You're dismissed. And no homework. No homework.